Thank you very much. So good afternoon, everybody. So it's quite a long title. So first I would like to thank my co-authors, which really helped me preparing this presentation, and I want to thank them for their patience. So I'm going to present to you the PP instrument. So PP stands for permittivity probe. Its objective is to measure the electrical characteristics of the subsurface of a nucleus of a comet. Knowing those characteristics can give us constraints on the composition, temperature, and porosity of the subsurface. Where's the... Yeah, okay. First I'm going to present to you briefly the theory behind the instrument and how we correct our data, and then I'm going to present our data with the preliminary and interpretations we have done of it. So the PP instrument is based off the mutual impedance probe technique. So if we have a ground with a complex permittivity, so with a real part that, which is the dielectric constant, and an imaginary part which is linked to the electrical conductivity and the frequency of our measurement. So what we do is we have 4 electrodes. We have 2 transmitting electrodes that will inject a sinusoidal current into the ground, and 2 receiving electrodes where we'll be able to measure the induced potential. And we can then, after, measure the potential difference between these 2 electrodes. So what we are looking for, well, we are looking for the phase, the difference in phase and amplitude between the injected current and the difference in potential. From those values, we can derive what we call the impedance, the mutual impedance of a system. So the mutual impedance is the potential difference over the injected current. We normalize this mutual impedance by the impedance in vacuum. And the real part of this normalized mutual impedance gives us the dielectric constant, and the imaginary part gives us the conductivity. Knowing these values, we can constrain the composition, temperature, porosity. As I said, we need 4 electrodes. On the Philae lander, we are lucky because we have access to 5 electrodes. We have 2 receiving ones on the feet of the lander, and we have 3 transmitting ones. One of them is located on the 3rd feet of the lander, and the 2 other transmitting ones are collocated with 2 other instruments, so the APXS instrument here and the Mupus pen instrument here. Why 5 electrodes? Well, this will allow us to sound at different volumes of the ground, and because our measurements, we sound up to 1 to 2 meters under the surface, and by having different sets of electrodes, we can sound different volumes. Our frequency range of our measurements go from 10 Hertz to 10 kilohertz. This choice was made mainly to detect the presence of ice. So here we have plot from Meteorological and collaborators of a dielectric constant of pure water ice as a function of frequency. And we can see that in our frequency range, and each curve represents a different temperature of water ice. So in our frequency range, we can see that the dielectric constant of water ice varies as a function of frequency and temperature. And this is very interesting to us because it allows us to really constrain those values. There's also active measurements we planned during the descent, and I'll speak about those later on. So in theory, it works quite well. In practice, we have to correct for a certain number of things. For example, we have the body of a lander that is in between our electrodes, and it's a conductive element, and it's going to influence our measurements. We also have an electronic circuit that links all the electrodes that will have an impact on our measurements. To correct for these, we have developed the capacity influence matrix method, which I'm going to describe to you how it works. So we are able to simulate a ground with a known dielectric constant and electrical conductivity. From this simulation, and we also have an attitude of a lander. Here I'm showing a very simple simulation where the lander is just horizontal to the surface. From this simulation, we are able to calculate the capacity matrix of the system. So this allows us to take into account the conductive elements close to the electrodes. We had to set the capacity matrix of the electronics, so that takes into account the influence of the electronics. We get a global capacity matrix. From that global capacity matrix, we have a simulated impedance of mutual impedance of the system. And then we are able to compare the normalized mutual impedance simulated to the measured one. We do this for multiple configurations of the ground and of position of a lander, and with that we can constrain these values and the attitude of the lander. So it was an instrument that has already been used previously on the Huygens lander to derive the complex permittivity of the surface of Titan. So if you're more interested in that, there's a talk by Michel Hamelin tomorrow where he revisits a bit of the data from that instrument. So now I've told you about how the instrument works. I'm going to talk about what we measured on during descent and on the surface of the comet. So during descent, we have 4 calibration measurement sequences. These calibration measurements will give us the mutual impedance in vacuum. This is very important for us because it helps us understand if there's an aging of the instrument. It will also, there was no measurements done with integrated instrument on the lander. So also this value will allow us to have a calibration measurement in a known environment, which is normally the vacuum. Then on the surface, we have 4 times the same measurement sequences. I'll explain later why they were the same, and this gives us the impedance on the surface. The measurements on the surface we're doing the comet every night with a 2-hour separation in between, approximately 2 hours between each measurement. So like I said, we need the calibration measurements. But what happened is during descent, so this is an example of a potential measurement, and as you can see, it is completely saturated. So we have no good calibration data for potential. And this is a big handicap for us because it really makes understanding our data much more difficult. Luckily for us, we had some good injected current measurements. So here we have a plot. So I'm not showing you all the injected current points we measured. I'm just showing you an interesting event. So here we have the injected. So the green points represent the current we inject. So we have amplitude of the current here as a function of time since the separation. The error bars are, we determined those because during the cruise, the measurements of the current were very stable. And so those are the error bars on our points. What I have done is I have simulated the lander in completely surrounded by an environment of a given dielectric constant. So the blue line represents the simulated current for a permittivity of 1. And the red line represents the same simulation but for permittivity of 1.5. The first thing we can see is that we seem to be in a that we're quite consistent with a vacuum or very near vacuum environment. Another interesting thing we can see is that we have a drop of current from these 2 points to these 4 points. This could indicate a decrease in the electronic density as a function of at this point. This is preliminary interpretation, and the work is still ongoing on this. So now I've presented to you the results during descent. I'm going to present to you what we measured on the surface. So in theory, the measurements need to be done with 4 electrodes. The thing is, the lander was not in its nominal configuration, and we were therefore in safe mode. Safe mode for our instrument implies that the measurements were done before the deployment of the 2 transmitting electrodes which are collocated with the 2 of the instruments. So we only have the plus X electrode that transmits a current, and the plus Y and minus Y foot that measure the potential. So in this case, what happens is the body acts as the second transmitting electrode, and this makes our simulations also more complicated. So PP did not perform a single nominal measure during the first science sequence, and also for our simulations, the attitude of a lander towards the ground needs to be very well known, and sadly, for the moment, we don't really know this. So I'm gonna talk. So I'm gonna talk about the current right now. So we have here. So it's a similar plot to what I showed you earlier. We have the amplitude of the current here as a function of time since the separation. Here we have the data points measured during the descent, and here we have the data points on the surface. So these are with the plus X electrode. The points I showed you earlier are these points here. So what we can see is there doesn't seem to be a very big variation between descent, the measurements during the descent, and on the surface. This seems to be consistent with a plus X that is not in contact with the surface or on the ground. What we can do is we can use simulations to try and constrain the minimum distance of plus X to a surface. And this is what I have done here. So here we have a possible position of a lander. So this has to be updated with the image Jean-Pierre showed earlier. I'll do that as soon just after Christmas. What I've done here is I've simulated the injected current as a function of the distance of the plus X electrode to a surface. So here we have a plus X electrode. I rotated the lander. The electrodes get closer and closer. And these are the points I measured. So we have the amplitude of a current as a function of the distance of the electrode plus X to the surface. So these are the green points we see here. What I've considered is I've considered that the injected current is influenced by the surface when it gets to a value that is equal to the value in vacuum plus the accuracy of our measurements during the cruise of a lander, the cruise of a Rosetta. So this is a preliminary analysis, but if we suppose that the surface is composed of pure ice, it means that the minimum distance of plus X to the wall would be 5 centimeters. More accurate models of the surface and of the position of a lander could change this value, but the magnitude should not change that much. Then we have the potential on the surface. So here we have the plus X foot, and we measure the potential on the plus Y foot and the minus Y foot. And here we have the ratio of the plus Y foot over the minus Y foot. And what we can see first of all is that we have a greater potential on the plus Y foot. This could be explained with a difference of composition, of temperature, porosity, but also the plus Y foot could be more in the air than the minus Y foot. We do not know exactly why there's this difference in potential between the 2 feet. Another interesting thing is if we look at the individual potentials of the electrodes, what we can see, so here I have plotted the temperature from the Cassé data temperature. So we see that on one foot, the temperature, on the minus Y foot, the temperature is quite stable, whereas on the plus Y foot, the temperature decreases. Here I have plotted, so the dotted line is the minus Y foot and the full line is the plus Y foot, and the 2 colors represent 2 different frequencies. What we can see is, so if we look at the dotted line, it seems quite stable through the decrease of temperature. Whereas if we look at the plus Y foot, it seems to decrease as a function of temperature. So we have an environment that changes, well, we have a dielectric constant of the surface that changes with temperature. So this could be same. It could be the same material that has a different dielectric constant at different temperatures, or it could be a composition that varies with frequency of temperature. We do not know how, and the analysis is still ongoing. And finally, here, so I have not shown you much of mutual impedance because for the descent we don't have the potential because the measurements are completely saturated. On the surface, I was still able to plot them, but the thing is we cannot use them as was planned because we don't have the Z0. And so the analysis is still ongoing for this. So in conclusion, well, the PP-SESAME did not perform nominally, but with more precise simulations, we'll be able to derive electrical properties of the ground. For that, we need to know as precisely as possible, the position of a lander, and future work would include some more sophisticated simulations. We also have a replica of the lander in our lab that we can do some tests with, and we also want to do some measurements of complex permittivity of cometary analogs. Thank you very much for your attention.
Okay, we have time for one question. Yes, you'll have to step to the microphone, please.
So the question I have is the change you see in the dielectric property, they are as function of the diurnal temperature, and do you see it in a cycle way that is correlated to the diurnal variation of the surface temperature, or just is correlated from the surface temperature?
For the moment, we have only correlated it to the temperature which were measured by the Cassé instrument in the feet. Yes, it would be interesting to try and correlate it to temperature of the surface, but we have to see if that is possible.
Okay, thank you.